Hey kiddos, today we write Taylor and Maclaurin series, and this is a way to write power series for any function. So last video we started with geometric series, and we were able to write a power series representation for those. And then we manipulated that geometric series and turned it into inverse tangent and natural log of 1 plus x. And so that means we can write power series for functions that look like any of those three, which is great, but not enough because there's plenty of other functions in the world. So that's where Taylor series come in. So they look like this. Like when you read the words for these kinds of questions, they say, write a Taylor series for f of x centered about, and then they give you some value, x equals something. This centered about is what we talked about last week with home base. So this is your home base value. And they look like this. So you have your function that you are given, and you're going to say that it's approximately equal to f of a plus f prime of a times x minus a plus f double prime at a times x minus a squared over 2 factorial. I know it looks like it's getting worse. It's the same thing. Every term is the same thing. So if we wanted to, but that seems ridiculous to do. Things to notice are this degree and your factorial and your derivative all match. So these are all first. These are all second, third. So extending this on forever, we could write a generic one that would look like f with an nth derivative at a, x minus a to an nth power, and then nth factorial underneath. So that's what we're going to do. We have to build these things, which means every time we have a question, we have to go take a bunch of derivatives. So let's go write one for sine. Because right now, my options are to manipulate one of these three. Well, sine doesn't look like any of these three. I can't turn inverse tangent into sine in some magical way. So I have to build a Taylor series from scratch. We're going to center this one. Let's just center at 0. Centered at 0. And let's go build. So the way I do these is I go find all my, I don't jump straight into a polynomial. You're going to miss something. You're going to drop a negative. You're going to do something silly. So let's go build all of our things. We need our function. We need its derivative. We need its second derivative. We need its third derivative. How many do we need? I don't know. Enough. I'm going to do 4 for this one. Turn them into Roman numerals. So our function is sine. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine, and then we're circled all the way back through. Those are great. We don't use any of those. Now we need all of them evaluated at x equals 0. So f of 0, sine of 0 is 0. Cosine of 0 is 1. This is negative 0. I felt stupid writing it, but I'm doing it anyway. This is negative 1 and back to 0. So now we're going to go build. There's my Taylor up there. So my first one is f of a, f at the center, f at 0 is just 0. So we've got sine. I'm going to write it even though I know it's not there because I want you to see all the pieces. Plus first derivative, x minus 0 to the first over 1. Plus 0. Plus, or minus now. 1, x minus 0 to the third over 3 factorial. And that's as far as I went. So that's kind of the best I can do right now. But if I start to clean, maybe I can see a pattern and maybe I can write more terms. So I think our Taylor, our power series expansion for sine is going to be, all of that just reduces to x minus, this thing cleans just to x cubed over 3 factorial. Then I had a 0, but I know what's coming next because I know about the derivatives of sine. I know it's just going to cycle through. So next I'm going to have a positive x to the 5th over 5. And then minus x to the 7th over 7. If I were to write this in a summation, it would look like this, where I need an alternator. I need x to odd powers, and I need odd factorials underneath. So this is the 4th series that you need to have in your memory because we use sine a lot. The next one we're going to do is cosine. So here's the thing. You're way more powerful than you know now. You have options now, which you didn't have before. Your options are to start with one you know, one that is in your memory, inverse tan, 1 over 1 minus, or natural log of 1 plus. And now sine. Sine is one you can start with. If the thing you're trying to build, if the function you were given does not look like any of the ones that are in your memory, then you have to do a Taylor series from scratch, which can sometimes be really tedious because of all of these derivatives you have to take. So the next one we're going to do is cosine, centered at 0. We're not always centered at 0, but we are for most of these today. So if I'm going to do a Taylor series expansion or any kind of power series expansion for cosine, I'm not going to do a Taylor series from scratch and start listing derivatives because I can manipulate sine and turn it into cosine. So if I have this one in my brain, in my memory, which I do, because even if I don't, I can just scroll up and look today. 5, 5. I'm going to do one more term. If I have that one in my memory, the way I can turn sine into cosine is by taking the derivative of everything. The derivative of sine is cosine. So I'm differentiating both sides of this equation. The derivative of sine is cosine. The derivative of x is 1. And now I've got a bunch of power rules to do. I'm going to pull the 3. So I have 3x over 3 factorial. This is going to be, 3x squared. This is going to be 5x to the 4th over 5 factorial. This is going to be 7x to the 6th over 7 factorial, etc. And then I clean. When I clean this, I get 1 minus, the 3's cancel, and I get x squared over 2 factorial. When I clean this, the 5's cancel, and I get x to the 4th over 4 factorial. And I get x to the 6th over 6 factorial. So it's identical to sine, except for cosine has only even powers, while sine had all the odd powers. And if you know anything about the shapes of these curves, sine is odd and cosine is even. So it should make sense that that's how their powers work out too in their power series. If I write it as a summation, it's going to look like this. So I need an alternator on it. I need only evens, and then I need even factorials. Note the parentheses around that 2n. All right, this is the 5th one to go into your memory. Last one more. Last one we're going to do is e to the x. So if I think about my options, I know these 3 series, and now I know sine and cosine as well. I cannot easily turn any of those 5 power series that are in my memory into an e. So I'm going to build this one from scratch. We're going to center at 0. So if I start listing, the reason this one's really quick to do is because when I start listing, here's my function is e to the x. When I start listing derivatives, it's just e to the x all the way down. So when I start evaluating them at x equals 0, it's just 1 all the way down. So now I build a Taylor series using the formula from above. My first term is just going to be 1 plus 1 times x minus 0 to the 1 over 1, 1 times x minus 0 to the 2 over 2, 1 times x minus 0 to the 3 over 3. I know these have factorials, but they don't matter until 3, etc. So cleaned up, very pretty. 1 plus x squared over 2 plus x cubed over 3 plus x, I'll do one more, etc. And as a summation, it's going to be this. So I have x to the n over n factorial. The degree and the factorial are the same. All right, last one to go into your memory. There you go. Two things real fast. All of these are centered at 0 because they're the basic ones that I need you to have in your memory. If at any point they center you somewhere else, all that really does is change right here. So if I had you center this exact same thing at 7, this would be x minus 7 and x minus 7 squared and x minus 7 cubed. So it changes right there, and then it changes these values that are out in front, your coefficients. Second thing, these are all called Taylor series. So this thing we built, where'd it go? Up here is a Taylor series expansion for a series. Maclaurin, which you also need to know, is the same thing. Maclaurin are always centered at 0. So if they ask you for a Maclaurin series, you just automatically need to know that that means centered at 0. They can ask you for a Taylor series centered at 0, or they can ask you for a Taylor series centered anywhere. But Maclaurin, they won't necessarily tell you it's centered at 0. You just got to know. All right, kids, let me know if you need anything.